This is a dramatic reading of Shoot It in the Head, a blog by the stand-up physicist, available on science2.0.com. I think of myself as a purple guy in the blue state of Massachusetts. Now, when it comes to proposals in science, I go for headshots. Nature doesn't care if we keep repackaging bullshit. And a well-fed bull does not run out of bullshit. So the only way to stop a science zombie is a bullet to the brain. And I know from my own experience that the easiest person to fool is myself. So I'm always on the lookout for bullets for subjects that I actually speculate on. I'm a poor student of my own personal history, so this is only like an approximation of the timeline of when these things happen. But in 1997, I got interested in quaternions based on a contest I sponsored for providing a brief definition of time. In 1999, I was the second person to figure out a road to the Maxwell equations using combinations of symmetric and antisymmetric quaternion operators. Now, the complexity of that result led me to my first efforts to unify gravity and EM, ignoring the weak and the strong forces, as many do, but really should not. And right after, right before, that's right, it was right before my 20th high school reunion, I actually found a really tenuous road to the exponential metric, as you see right there. I mean, I love the exponentials. I mean, that's a calling card of deep insights into physics. And this metric is actually consistent with weak field tests, but differs at higher order tests. I mean, that's the gold standard, right? Experiments for the first order bending of light near the edge of the sun pitted Newton's scalar potential theory of gravity versus Einstein's rank 2 metric theory. And the predictions were differed by 100%. Newton had the low bid of like 0.875 arc seconds, and Einstein doubled down on that, predicting 1.75 arc seconds of bending, actually after an initial paper claimed the same result as Newton. And the first results from the solar eclipse in 1919 gave Einstein the victory. It was actually a little bit questionable there, and it actually took work with radio astronomy to really get that result solidified, like in the 60s or something like that, because they didn't have to rely on an eclipse when using radio astronomy. So Newton's scalar potential theory has but one term to warp time, effectively being this G00 term of the metric. Now Einstein had another equal contribution that bent space. So pessimists are going to say, well, Newton got the theory wrong. They don't even give him credit for half right. But optimists will say that no, actually the prediction is half right, and well, that's good for something. Now, second order light bending requires a measurement literally 1,000,000 times more sensitive. That experiment has yet to be done. The Schwarzschild metric predicts an additional 10.8 micro arc seconds more bending should be viewable. Now, if the exponential metric rules the heavens, then the experimentalists will see 11.5 5 microarcseconds more bending, a 6.6% difference. Now, the state-of-art's measurement is about 100 microarcseconds, a great 10,000-fold improvement over what was done in 1919, but still 100-fold improvement is needed for me to tell the difference between the exponential metric and Schwarzschild. And there's another problem though, and that is the sun spins, and it might have this quadrupole moment. Either effect could actually drown out that 6.6% difference. Now, I actually spent years on a science news group, Sci Physics Research, pounding the drum for the exponential metric because it was actually solutions to some differential equations. It was consistent with current tests. It was different at higher resolution. I thought that triple play would get some interest. I mean, triple plays are rare. I had a specific testable hypothesis, while the work on strings to this day doesn't have that much. Now, alas, people really are into their own areas of study, or they're kissing cousins. Rank 1 proposals for gravity are the work of idiot savants without the savant part. Now, in 2004, I actually saw a bullet with the exponential metric's name on it. Now, it was really, I had this funky derivation, right, of the metric, which relied on perturbation solutions of a potential equation plugged into a force equation, rearranged to then look like a metric. I mean, that's going to be hard to sell to someone formerly trained, and I don't blame them. Okay, I mean, I knew that was odd. Okay, it was something, but odd. Now, I also had field equations done the right way, derived from the Lagrange density using the Euler-Lagrange equations. But I had yet to take my exponential metric and see if it solved my field equations. Now, I actually remember this particular walk from 1340 Com Ave to my gym. I had only a vague idea how to take the exponential metric and see if it solved my field equations. Okay? I didn't sweat those details on this walk. No, I was worried about the results of such a calculation. I mean, let's say I did figure out how to plug the exponential metric into my field equations, and it came back as being plain old wrong. Well, that did get me sweating before I got to the gym. I've been talking about the exponential metric for years. Actually, for 4 years, if you want to be that precise. And I remember the realization I had in front of Natalie's Pizza. If the exponential metric does not solve my field equations, then I would have to announce those results on Sci Physics Research and on my website, quaternius.com. That's a nice, clear line of action. But there was a backlash in my brain. I didn't want to have to do that. I really wouldn't have to do that, would I? Yes, I would. Think about anybody else who's reading up on my claims in Sci Physics Research about the exponential metric. If and when I found a deadly flaw, I would be obligated to describe it in order to save other people from wasting effort in that direction. So by the time I reached the gym, I knew I would have to fire a bullet at the exponential metric and report the results. So for 3 weeks, I did nothing. I was actually waiting for my mind to settle down, accept that, this would be the consequence of doing this sort of calculation. I also didn't know how to do the calculation. There was a big disincentive to actually learn how to do the calculation. That might end up making me result about report a failure. 4 years of work. Let's not do that. And I was like, no. And this 3-week period said, no, this is not about me. No. This is about nature. Okay? She does so in so much in simultaneous silence. Just right now we've got light going on, we got gravity going on, we got the nucleus stuff going on, maybe a little beta decay, real small amount, all in this room, all at the same time, while we're spinning around a galaxy. The number of things that are going on simultaneously is insane, and she's doing it all perfectly, I was just in the deep end of the pool, and I don't have any swimming buddies, as happens in graduate school. Well, at least I wasn't in the basement. I was living on the second floor, with a view of 1325 Comm Ave, Aerosmith's first place in Boston. So I'm going to try and set the stage in that 3-week period, kind of knowing the calculation to do, just missing some absolutely essential details. And so this is the first of my 4 field equations that I was going to have to try and figure out how to plug my metric into. Okay, and only the sign on that Laplace operator changes relative to good old Gauss's law. All right. Now, fringe physicists before me have constructed a mountain of Maxwellian gravity crap. Okay, so there's so much crap about Maxwell and gravity. I can understand why a pro would just get nowhere near this sort of thing. And in the static case, it just actually becomes Newton's law of gravity. All right. So, and that is the sort of problem that you give to high school students, just starting out in calculus, show that a charge over R potential is actually a solution to that differential equation. Now imagine that potential is actually constant, not a 1 over R. Can you find a solution if the charge density is not 0? So take a close look at that. We're saying rho's not 0, but phi there is constant on the bottom line there. And you go, what? Is this a trick question? There's nothing left to do if the potential is constant. Well, that is the case for the tools provided in high school. All right, the derivatives they teach first are all about the function and how it changes. And it's a completely reasonable place to begin an education. But then you learn that mathematicians, man, they thought about taking derivatives if the background geometry was changing. Somebody is playing with a graph paper and stretching it and pulling it and doing all kinds of crazy crap. So if that's the case, then one needs to use a covariant derivative. All right, a covariant derivative has the normal derivative, okay, plus something else. Oh no, actually it's called a connection. Okay, so that partial derivative there really is the thing from high school. That capital gamma there is called a connection. And it completely accounts for the changes in geometry. So just stuff it in another thingy. That can't be that hard, can it? Oh yeah, it can be impossibly hard to understand. that is something that mathematical heavyweights can play all kinds of games with. And they actually do so in papers that I don't understand. Okay, but I use the playbook of general relativity. Now, the connection there is metric compatible and torsion free. And you say, what? I basically spent 4 or 5 months with Sean Carroll's lecture notes on general relativity, which you can download for free on the internet. Just do a search. That actually just gave me a sense of what those technical constraints mean. I didn't have to take any tests because I probably wouldn't have done very well. The bottom line is that the connection bears the name, for at least in general relativity in my own work, of Christoffel symbols of the second kind. That does sound a little bit like a Steven Spielberg movie. Now, we live in perfectly flat spacetime. Oh, no, not perfectly. It's close to perfect, okay? Now, to be super right, I could view the Laplace operator as being two covariant derivatives with two kind of connections going on there. Now, but I was actually skeptical of that approach, remembering a lesson learned early on in quantum mechanics, where if one used two relativistic derivatives, the equations really didn't describe a hydrogen atom. That was actually for relativistic quantum field theory, a valid subject, but not for ordinary atoms sitting around in a room. So for almost perfectly flat spacetime that like we live in and we describe mostly when dealing with the cosmos, except for black holes, I thought what I should do is take a normal divergence of a covariant derivative of a potential. What did he say? Okay, he said that. Okay, so there's really only one kind of a connection, one Christoffel symbol coming into play. So the Christoffel actually takes 3 different first-order differential equations of a metric, and the divergence of a Christoffel will then take the second-order derivatives of a metric, and that's actually the minimum required to constrain a metric by physical connections, a second-order differential equation. So think of that as kind of like being Newton's second law for space-time geometry. Okay, so that's kind of where I was stuck for 3 weeks. I'd never calculated a Christoffel symbol for any metric. I was not sure I was going to be able to do the calculation. I was just quite insecure on the subject. Plus, I was scared of what the result could be. But I recall it was a nice Saturday morning, and I was wondering, what should I do this morning? And it's like, oh yeah, I got that calculation. Well, maybe I should crack open a book. Now, I happen to have good luck with this particular book, Gravitation and Space-Time, 2nd edition by Ohanian and Ruffini. Other people have their own personal favorites. I'm not going to say you must read that book. Oh, where did that go? Oh, and this was the page. This was the page right in here that defined the Christoffel symbol of the second kind. And I know I wrote it out. There it is. Ooh, and you go, that's kind of scary. Okay, so, I was like, yeah, but what am I really going to do with that? I really started reading all kinds of books, anything I could get my hands on these Christoffels, and I found out that one of the these 3 metric derivatives in here, one of these 3 guys goes to 0 if your metric is static. I was like, yeah, that's nice. I like it when that's a little less complicated. Then I found out that another one of those goes to 0 if it's diagonal, which was what the exponential was. So it's like I only got one to deal with. How nice is that? And so that was looking good. Instead of 3 derivatives of a metric, I was down to 1. Okay, and then it was like, yeah, but I've got the exponential metric, and even decades later, I actually remembered what the derivative of an exponential is. It's the derivative of that exponent times the exponential. And then the gamma thing is just like the inverse. Well, the inverse of an exponential just throws a minus. And it's like, oh, so let's see. That top line is the derivative rule for exponentials. You get out the derivative of the exponent times the exponential of it again. Then when we take the gamma thing, oh, I get a cancellation of the exponentials. How sweet is that? And so really, if I'm going to take the divergence of the gamma of the exponential metric, divergence, of the kind of Christoffel, then I basically get something that, well, good old Laplace would actually recognize. It's a charge over our potential. Laplacian operator on a charge over potential. It's like, how perfect is that? I was like, whoa, that was just amazing. One of the more amazing experiences in my intellectual grill, seeing that worked out. Now this is just a sketch. Details can kill, like a sign error, factor of a half. And so I actually run the exponential metric through Mathematica using functions that James Hartle developed for that program. And in section 4, like page 7 in an HTML document, PDF, a notebook, I'll leave the links on the description of this YouTube video. You can just go and check it out yourself as a cross-check. But just as important, actually, was that I told a friend of mine about this issue who actually liked to work with general relativity and covariant derivatives to see if he could independently confirm the observation about the exponential metric in Gauss's kind of gravity law. And he came back and he said, no. It did not work. So I said, bummer. Let me go over the details with you. And he, sure enough, had done 2 covariant derivatives. When he did just one, the divergence of one of them, then it did work. So that was actually quite a nice confirmation, I thought. Now, I remember reading in one of my GR books that one should never bother to take the divergence of a Christoffel symbol. No, don't bother. The calculation is banished because the Christoffel does not transform like a tensor. Now, fortunately, I'm doing something different. I'm taking the divergence of a covariant derivative of a 4 potential. The 4 potential is constant while the metric is dynamic, thus reducing the problem to the divergence of a Christoffel symbol. Did I tell you that my father went to Harvard and Harvard Law School, as did his father? Yes, well, I got waitlisted. So I went to the tech school down the road, which was actually my first choice. What is cool about this observation is that Newton's old scalar potential law for gravity, can be expanded easily enough to a 4 potential. I mean, those are the 3, they're doing nothing, right? The exponential metric is not a solution to the general relativity field equations. So we got some competition going on here between the 2. Now, in 1919, Einstein's gang of 10 equations beat Newton's scalar theory. Now, in 2011, a 4-vector Newtonian gravity proposal could actually challenge Einstein's work for a rematch. This time it's Newton's theory that predicts more bending. Go Newton! So the exponential metric survived this potentially deadly calculation. So here's the snarky puzzle. Let's say you're going down in a gravity field. Somebody's watching you do this, okay? And they're going to say about you that your clock is ticking a little slower, your ruler is getting a little red shifted there. Now, as far as you're concerned, remember, your ruler is normal, your time is normal. This is the outside guy talking trash about your system of measurements. That's two changes, all right? 1, 2. We're good at counting. So Newton's scalar theory, let's say that involves just one thing, doesn't cut it. It can't explain both effects. So I want you to write a four-potential theory that could account for both the G00 term. Oh, guess what? You don't have to change anything. Oh, and the GRR kind of effect that gravity has. So if you don't actually want Newton to do everything, you could actually combine a Newtonian potential with a bit of metric. Now, since mixing potential theory with dynamic metrics is blasphemy, expect to take a bullet for the team. Thank you very much.